An autoencoder functions as an artificial neural network focused on grasping effective codings for unlabeled data. It works through learning an encoding function that transforms the input data and a decoding function that reconstructs the original data from the encoded version. This process allows for the creation of a compact representation for a dataset, often for reducing dimensions to produce embeddings for further use by different machine learning models. Various types of autoencoders, such as regularized versions like sparse, denoising, and contractive autoencoders, are adept at learning representations beneficial for subsequent classification tasks. Variational autoencoders, another type, can operate as generative models. In terms of components, an autoencoder is defined by two sets: the space of encoded messages Z and the space of decoded messages X. Typically, these spaces are Euclidean, with X as R superscript M and Z as R superscript N, where M is greater than N. The autoencoder consists of two groups of functions. First, the encoder group E sub phi I maps X to Z and is parameterized by phi I. Second, the decoder group D sub theta maps Z to X and is parameterized by theta. During operation, the encoder transforms input, usually through a multilayer perceptron structure, into a code, while the decoder produces the decoded message with the assistance of activations and weight matrices. For training, the quality of an autoencoder is gauged by a task, represented by a reference probability distribution over X, and a function measuring the reconstruction quality between inputs and outputs. The process of determining the optimal autoencoder involves minimizing a loss function achievable through mathematical optimization, commonly gradient descent. This optimization quest is commonly known as training the autoencoder. An example of a reference distribution involves an empirical dataset, allowing for the calculation of the L2 loss function and engaging in least squares optimization to search for the optimal configuration of the autoencoder. An autoencoder functions effectively with an encoder reducing the dimensions of the input data into a code and a decoder reconstructing the message from this code. An undercomplete autoencoder is characterized by a lower dimensional code space than the message space, compressing the information. Conversely, an overcomplete autoencoder may fail to learn useful features if the code space is equal to or larger than the message space or insufficient constraints are present. However, studies have shown that overcomplete autoencoders may still extract valuable characteristics. Fine-tuning the code dimension and model capacity based on data complexity is crucial, often achieved through modifications to the basic autoencoder structure. Variational autoencoders, VAEs, fall under the category of variational Bayesian methods. They operate differently than conventional autoencoders in terms of both their design and mathematical framework. In a VAE, the latent space is a mixture of distributions as opposed to fixed vectors. The main goal when working with an input dataset X and a multivariate latent encoding vector Z is to model the data as a distribution p theta of X. This is determined by a set of network parameters, theta, and is represented mathematically as pp theta of X equals the integral over Z of pp theta of X and Z with respect to Z. Sparse autoencoders, abbreviated as SAEs, are inspired by the sparse coding theory seen in neuroscience. These are variations of autoencoders where the codes, noted as E, phi of X, tend towards being sparse. This means that most of the entries are close to zero. Although SAEs might have more hidden units than inputs, only a select few hidden units are allowed to be active at the same time. This selective activity enhances performance on classification tasks. There exist two primary methods to uphold sparsity within SAEs. The first approach involves constraining all but the top K activations of the latent code to zero, characterizing the K-sparse autoencoder. Alternatively, a relaxed version of the K-sparse autoencoder integrates a sparsity regularization loss into the optimization process to enforce sparsity based on a designated weight parameter measuring the desired sparsity within each layer. The sparsity regularization loss comprises a weighted sum of sparsity losses across all layers within the autoencoder architecture. The enforcement of sparsity can be achieved through various functions such as the Kullback-Leibler divergence, L1 loss, or L2 loss for measuring sparsity deviation. Another strategy involves emphasizing as much sparsity as possible without referencing any specific desired sparsity, encapsulating this concept within the sparsity regularization loss formulation. A denoising autoencoder, abbreviated as DAE, is a model designed to create a robust representation by changing how it reconstructs data. Initially called a robust autoassociative network by Mark A. Kramer, a DAE trains by intentionally corrupting input data of a regular autoencoder during its training phase. This corruption is done using a noise process defined by a probability distribution mu subscript t over functions t from x to x. Through this, the DAE aims to reconstruct the original, noise-free input from a noisy version of the input. The optimization problem involved in training a DAE is focused on minimizing the loss function L, open parenthesis, theta, comma, phi, close parenthesis, equals, expected value, sub x drawn from mu sub x, comma, t drawn from mu sub t, of bracket, d, open parenthesis, x, comma, open parenthesis, d sub theta, composed with e sub phi, composed with t, close parenthesis, open parenthesis, x, close parenthesis, bracket. The goal is to reconstruct the original input without noise, hence the name denoising. Various noise processes are employed during training, such as additive isotropic Gaussian noise, masking noise, and salt and pepper noise. The effectiveness of DAE relies on the assumption that input data have stable representations resilient to common types of noise, and that these representations capture meaningful structures within the data distribution for the intended tasks. In contrast, a contractive autoencoder, abbreviated as CAE, introduces a contractive regularization loss to the standard autoencoder loss function. The objective is to enforce a certain level of contractiveness, indicated by the parameter lambda, which is greater than 0. This regularization loss is determined as the expected square of the Frobenius norm of the Jacobian matrix of the encoder activations concerning the input. The CAE works to ensure that small changes in the input data lead to minimal variations in the coded representation, promoting stability and robustness in feature extraction. By adding the contractive term to the loss function, the CAE aims to enhance the model's ability to maintain consistent representations under different input perturbations. Further along the spectrum of autoencoder variations, we encounter the minimum description length autoencoder, MDL-AE, a sophisticated adaptation of the standard autoencoder architecture. Drawing from concepts in information theory, particularly the minimum description length, MDL principle, the MDL-AE emphasizes creating a concise and informative representation of data. Following the MDL principle's premise that the best model should offer the most compact encoding of both the model and the data, the MDL-AE minimizes the overall description length of data, combining the size of the latent representation, code length, and the reconstruction error. This approach ensures that the learned representation is not just efficient, but also interpretable for reconstruction purposes. One notable variation is the concrete autoencoder, CAE, tailored for discrete feature selection requirements. The CAE restricts the latent space to a defined quantity of features chosen by the user. This model incorporates a continuous relaxation of the categorical distribution to facilitate gradient flow through the feature selection layer, enabling standard backpropagation to determine the optimal subset of input features that minimize reconstruction errors. Autoencoders are commonly trained with a single-layer encoder and a single-layer decoder, though employing deep encoders and decoders presents numerous advantages. The use of deep networks can significantly reduce the computational cost of representing functions and decrease the amount of training data necessary for learning certain functions. In practice, deep autoencoders have shown improved compression capabilities when compared to shallow or linear autoencoders. The technique for training many-layered deep autoencoders was developed by Geoffrey Hinton through the deep belief network method. This approach involves treating each adjacent pair of two layers as a restricted Boltzmann machine for pre-training to approximate a good solution, followed by fine-tuning using backpropagation. There has been a debate among researchers regarding whether joint training the entire architecture at once with a single global reconstruction objective is more effective for deep autoencoders. Studies have indicated that joint training can lead to better data models and more representative features for classification, but its success heavily relies on the regularization strategies employed. Historically, autoencoders have origins dating back to the 1980s, when generalized PCA to autoencoders was introduced. Over time, the concept transitioned from typical applications like dimensionality reduction and feature learning to becoming widely used for developing generative models of data. Notably, autoencoder modules became a component of prominent AI systems in the 2010s, featuring in models like VAE in Stable Diffusion and discrete VAE in transformer-based image generators such as DAL-E1. The terminology surrounding autoencoders during their early inception varied, with names like identity mapping, auto-associating, self-supervised backpropagation, or Diabolo network being used interchangeably. Autoencoders find application in diverse fields, with two primary areas being dimensionality reduction and information retrieval. Dimensionality reduction serves as one of the foundational applications of deep learning, supporting tasks like improved performance in classification by placing semantically related examples closer together. In the context of information retrieval, autoencoders have contributed to enhanced search efficiency in low-dimensional spaces, notably in applications like semantic hashing. Another notable application of autoencoders is in anomaly detection, where the model's ability to precisely replicate salient features from the training data aids in flagging unfamiliar anomalous instances by analyzing reconstruction errors. Autoencoders have also proved useful in image processing, excelling in tasks such as lossy image compression and image denoising, with applications extending to medical imaging for tasks like super-resolution and disease diagnosis. In the realm of machine translation, autoencoders have been incorporated into NMT systems, enhancing the encoding and decoding of text for multilingual communication. Communication systems leverage autoencoders to encode data robustly for channel impairments, optimizing end-to-end communication performance and overcoming inherent challenges in modeling real-world channels accurately.